Looking at our picture, we've talked a little bit about the energy, which we keep coming back to. We've discussed the atoms. We've discussed the composition. We started talking about the bonding, just basic bonding, one atom bonded to another one. What we want to do is we want to start having multiple bonds. Instead of just having one atom bonded to one thing, we want a material. We want thousands, millions, billions, trillions, significantly more than that even, bonds within a material. And so we're really going to start looking at, yes, it's bonding, but we want to look at the microstructure, how the entire thing comes together. So first off, we want to kind of start with what are the states of matter. There are the three common ones that we learn when we're young: solid, liquid, and gas. There are other ones, and they keep finding new ones periodically. Some of them are subsets of other states of matter. But really what I want to get down here is material science focuses mainly on solids. They're materials, and that's what materials are made out of. They're made out of solids. Occasionally it'll go into some of the more obscure states as well. But for the most part, we stick with solids until you get a little bit further maybe into material science, if that's what you're interested in. All right, so there are two ways that we can have a solid. And let me go ahead, we're going to fill out this chart. If I have a solid that is ordered, certain things are going to happen. Or I could have a solid that is disordered. The atoms in it don't have a good order. And those are going to have certain things. So that's what we're going to discuss here. If I have an ordered solid, the atomic arrangement, the arrangement of the atoms in it, are regular. There's a regular pattern throughout the entire system. With that, the type of order that I have then is going to be long-ranged. It's going to go throughout the entire material. So regular pattern, this pattern continues on for a long time in multiple directions, not just in one direction, so in 3 dimensions. And then we want to give a name to this because we want to make sure that if I'm going to have these two things that I'm discussing, I have ordered solids and disordered solids, that I can easily identify which one I'm talking about or what's happening. The name that we give to ordered solids are crystals. We can say that a material is crystalline. And sometimes for shorthand, you might see XTAL for crystal. It's just a faster way of writing it, crystal. All right, so let's go on the other side. What about disordered solids? We're actually not going to talk a whole lot about disordered solids outside of just kind of filling out this table. In this video, we're going to get into them in one of the next few videos. We'll talk about them. But since we're filling out this table and we're discussing there are these two different types, I at least want to make sure that we have a starting point. So for disordered solids, the atomic arrangement is going to be random. They're not going to be ordered. And if there is some type of order, it's only going to be short-ranged. And so there might be a little bit of order here and there, but when we're talking about, so many atoms, even if there's a little bit of order, if it's short-ranged, it's really not very ordered at all. We call these materials amorphous materials. Or we call them glass. Now, I want to make sure that we understand here that glass does not mean that transparent thing that we use for windows. That is what we call glass. Have have a glass of water here. There's glass in windows. We have glass as a material all around. When I'm talking about a type of material, a type of solid, and I say that is a glass solid, what I'm talking about is it's amorphous. It gets a little bit confusing, and so we'll try to really be distinct when we're talking about whether we're talking about a material that just has a random structure or whether we're talking about glass, such as something I'm drinking my water out of, or the windows in my house or my car. So we will want to make sure that there is a distinction between those. But right now, what we're really going to talk about in this video is we're talking about the ordered solids. All right, so we're going to not really get into any specifics. You can if you want. It's actually very interesting things, but much of science is really driven by civilization growth and war. Not just war by itself, but when a civilization is growing, and there might be some war as well, because that's how civilizations in the past have grown, is by conquering and taking over. And the civilization that has a little bit more technology will be the one that is most likely going to win, and you get that technology by thinking and studying. All right, so this is kind of the 16th century on, and that's really when we've really had a lot of what we consider our modern science beginning. And I threw some names down here, and you can look some of these names up. I forgot to put a parenthesis there. But we have this here. We can start saying even back in the 16th century, wars were being fought, and they wanted to have the best possible way of winning, and they had these things called cannons that they started using. Cannons needed these cannonballs. They were spherical, and to make sure that you could have a lot of them, I mean, that you have these balls sitting around, they're going to roll around, they're going to make a mess. You got to get them from point A to point B. You got to stockpile them somewhere. You want to make sure that you can stack them efficiently. You want to be able to transport them efficiently. You don't want them making a mess. You don't want them rolling around. You don't want them falling over. And so a large portion of trying to win a war at that point was saying, if we can just figure out how to have more cannonballs and be able to keep them efficiently stacked and transported and stored, we're more likely to win. And so mathematicians figured out what are the best ways to stack these cannonballs. A little bit later, we looked at atoms as being hard spheres, and that's what a cannonball is, and it really doesn't matter on the size. A sphere is a sphere. It doesn't matter if it's on the size of an atom, the size of a baseball, cannonball, or the size of planets. If I'm going to stack them, as long as they're all the same size, they're going to stack pretty much the same. There were people that looked at minerals, such as quartz crystal, and they noticed that it had the same angles on corresponding faces. They'd have multiple samples, and they'd say, hey, this one has these angles on these faces, and if I orient this other crystal so that the faces are similar, it has the same angles as well. They looked at calcite, and they noticed that there were similar shapes, and it didn't depend on the size of the mineral. You could have this really big calcite crystal, and it would have a certain shape, and you'd find a smaller one, and it would have the same shape, and you could break it, and it would have the same shape, and you'd break it again, and it would have the same shape. And so they started seeing that there were a lot of things going on here with materials and how they were structured, and what they might have been looking at, what they eventually figured out they were looking at. I don't know if they were going into it thinking about this, but they were looking at the microstructure. After a lot of math was done, it was figured that in 3 dimensions that there are 7 space-filling volume elements, and we call those the 7 crystal systems. And I'll talk a little bit more in just a moment about what that means. And lastly, there are 14 ways to arrange atoms in these space systems, these 7 crystal systems. We call those the 14 Bravais lattices. All right, so what is a space-filling volume? Well, to make things easier, instead of thinking about volumes, let's think about things in terms of 2 dimensions. So if I wanted to fill a floor, a plane, with 2-dimensional shapes, such as I'm going to put tile on the ground, what types of shape can I fill completely without there being any gaps? Now, I don't want to say I'm going to pick multiple shapes. If I could only pick one shape, what shape could I use to where I have no gaps at all? And I'm going to divide this in half here. And I'm going to put things like squares on this side. And if I lay squares down side by side and then, up and down and all different directions, I can lay tile and it's going to not have any gaps on it, especially if it was a perfect square. Obviously, my drawing's not that great. If I have an equilateral triangle, I can do that. If I have rectangles, I can do that. If I have hexagons, I can do that. And I can repeat these structures over and over in all directions, two-dimensionally, and I can fill the floor with tile, and it is going to make sure that I don't have any gaps anywhere. And that's what we mean when we say that there are space-filling elements. Now, in this case, it's two-dimensional, so it's area-filling elements when we're talking about 2 dimensions. We'll get to 3 dimensions in just a minute, but it's just much easier to think about these things in 2 dimensions. But there are going to be some shapes where I can't fill in 2 dimensions. Circles. I can lay circles together and there's going to be gaps. They're not going to be able to lay perfectly right next to each other. Pentagons. I might be able to lay them around somewhat, but eventually I'm going to have some little triangles, some little gaps somewhere that I'm not going to be able to fill. And so there are shapes that will fill and those that won't. And that's in 2 dimensions, just a little bit easier to understand. What they found was in 3 dimensions, there are 7 shapes that I can use, or that anybody can use, to fill a volume without any gaps whatsoever. And the idea of these 14 ways to arrange the atoms in that space is within there, if I want to keep some symmetry, where can atoms be within those volumes, within those 3-dimensional space-filling volumes, so that I could repeat it over and over. All right, so what I want to do, let's think about things in 3 dimensions. I have an analogy here. I have a box on a pallet. If you've ever worked at a warehouse, maybe a grocery store, or a distributor of some type, you've probably dealt with this. If not, maybe you've seen it before. But what I have here is I have a pallet, and I have some nice cubic boxes on this pallet. And inside of here, let's say there are cans inside each of these boxes. The crystal structure tells us where the boxes are on the pallet. I have a box right here on this side. I have one next to it. I have one next to that. I have one next to that. I have ones on top of it. I have one up here. And really with the crystal system, what it means is if I know where one is, I know where this box is. What that means is I know where every other box is. It's going to be a certain number of integers, either to the right or left, forward or backward, or up and down, or a combination of those. But because it has a regular pattern, I can with confidence tell you that there is a box somewhere. What the lattice tells us, right? The distinct ways to arrange the atoms in space. In this analogy, what the lattice tells us is where are the cans that are inside these boxes. And so if I have this box, and inside each box I have 4 cans that are stacked something like this, not only can I tell you where each box is at, but now I can tell you where every single can's at. I know that there is a can sitting in this top corner of this box right here. And I guess if there are 4 of them, it's a tall, skinny can sitting right there. Well, that means that I can tell you where every other can is inside of here. There's one right next to it. There's one right next to that. There's one right next to that. There's one's diagonal. And that's the idea of what a crystal system is. It's where these boxes are. And the lattice tells us where the individual things within the boxes are. And in our case, the boxes are our unit cells. And the cans, the things inside those boxes, are going to be our atoms. All right, so when we crystallize anything in 3 dimensions, it must form one of these 7 structures. It has to. And within those 7 structures, it has to arrange in one of the 14 Bravais lattices. That is just what has to happen. And that doesn't matter whether it's atoms, molecules, things like proteins or DNA. If I wanted to work at a grocery store, and if I was setting out the produce, I was dealing, let's say, with oranges or something, and I wanted to set the oranges in a crystalline pattern, I would have to pick one of these. All right, so this is something I found online, and to be honest, I don't really necessarily like this. It's not perfect, but it's a pretty good one. It's one of the best ones that I've seen. There are a few things I would change if I were to come up with it. I've been thinking about writing my own. I just haven't. But this is a good one for a good reference. There are 7 crystal systems here, and those are listed on the left-hand side. Triclinic, monoclinic, orthorhombic, tetragonal, triagonal, cubic, hexagonal. And each one tells you kind of what the parameters are. The most simple one that we discuss a lot is the cubic system. And the reason we like that one is it's easy to use, and there are actually a lot of materials that we use on a daily basis that fit in that system. And so it's not necessarily like it's a bad one to talk about. It's easy to use and it's common. Cubic, meaning that all my sides are the same. My A1, my A2, and my A3, those would be like your lengths, widths, and heights. And my angles are all the same. So they're all 90 degrees. That's what makes it a cube. If you look through here, you see that there are other ways to do it. This first one is triclinic. It has different lengths, widths, and heights for all the sides, and none of the angles are similar as well. That is one way to fill up a volume. If I have them, and they all have my A1s are all the same, my A2s are all the same, my A3s are all the same, all the angles are similar, and I stack these together, I have a whole bunch of things that look like this shape. I can stack them forever in every direction. I won't have any gaps anywhere. And I can do that with all of these. For the most part, I want to talk about the cubic one. There are 14 ways to arrange these atoms inside of these 7 crystal systems. So here are my 7 crystal systems here, and if we count, we have 14 pictures here. That's because there are 14 ways to arrange atoms within these systems. For a lot of them, for all of them, we have what's called the simple lattice. And what that does is it just means that I'm going to have an atom at every single vertex of my shape. I have my volume centered, and what the volume center does, it says I still have an atom at every vertex, at every corner, but I also have one right here in the center. Sometimes instead of volume centered, it's called body centered. We have the one that's called base centered. There are, again, ones at every corner or vertex, and there's an atom on the base. Then I have face centered, again, one on each corner, but each face also has an atom. Each face, here's a cube, each face of the cube has an atom on it as well. It takes a little bit of time to kind of process this and think about it and see what's happening. There are some better pictures. This one just kind of have dots. You can find ones that you can actually see the hard spheres. You can see how they sit into there. We're going to practice sketching some of those as well. It's good practice to do that. All right, and again, because if I do have a perfect crystal, I can easily determine and know the position of every single atom and molecule within any material. And again, be careful here. This is for a perfect crystal. Eventually, we're going to start talking about imperfections and how that affects things. But for now, in a perfect crystal, we can easily determine every position of every atom, because once I know what this crystal structure looks like and this Bravais lattice looks like. I can repeat it in every direction, which means I can simply just see where things go. These little boxes here that have these atoms in it, we call the unit cell. Unit cell is the smallest group of atoms or molecules that contain the overall symmetry of the material. And we can repeat these to build a three-dimensional material in all directions. Some things that are important about the unit cell is we could know the volume of the cell. That would be like this, the volume of the cube here. What's the actual volume that the cube makes up? We could know the packing density. The packing density, we're actually going to calculate some of that in a bit. The packing density talks about how much of this cube is filled with atom compared to how much is empty space. We could know the lengths of the edges. Those would be my A's here. We could know the angles of the corners. Those would be my alphas. We could know the number of nearest neighbors. So if I look at this atom in the corner right here on this simple cubic, my nearest neighbors are the ones that are along these edges here. And we got to remember that this is in three directions, so they'd be coming the other way as well. We'd want to know the distance and the directions to them as well. We could also need to know maybe the number of second nearest neighbors. Maybe we don't want to know which ones are the closest, but which ones are the second closest. What's the distance to those? What's the direction to those? So all these things can become important. There are other things that we could probably want to find out as well. All right, so the types of Bravais lattices we've discussed already. We have the simple structure. That's the one where we have the atom or molecule at each vertex or corner. We have the volume or body-centered. That is where we have the same simple structure, again, the one that has one on each corner, plus we add an atom in the center. We have the base-centered, which is a simple structure, plus atoms on the center of the base, and the base is also considered the top, so the top and the bottom. And then the face-centered, it is the simple structure, plus we have atoms on the center of each face, not just the base, but on each face. So in the case of a cubic, that's going to be 6 faces that we have an atom. Within the Bravais lattice, within each one, there can also be some more complexities. And so here's just a quick overview. And remember, this is just an introduction on crystals. The following are all face-centered cubic. And so let's scroll back up really quick. That would be this picture here where I have an atom on each corner and I have one on each face as well. And so some examples here would be things like some of my metals, whether it's aluminum or copper. They're made up of atoms, and they do make that face-centered cubic crystal. I could also make this with a molecule, something, let's say, like methane. If I cool off methane really, really cold and I'm able to crystallize it, it's going to form in this crystal structure as well. This crystal structure, again, looks like this, but instead of having an atom on each corner and on each face, the atom, this little dot here, is the actual molecule. So this dot here is actually the entire methane molecule, and each dot on here is a methane molecule. We have NaCl, and that's going to be an ion pair. We call that the rock salt structure, and each spot on the each dot here is an ion pair. It's a pair. At this dot, there is going to be an Na and a Cl. We'll get into that when we talk about ceramics. That's a hard one to visualize, but I will talk about that one in a later video when we get into ceramics. We could talk about diamond made of carbon or silicon. Those are atom pairs. They do make the FCC structure. We call that the diamond cubic. So lastly, what we want to do is we want to start talking about the packing density, sometimes called the atomic packing factor. And what that does is that tells us how much, what percentage of the unit cell is made up of atom. So how much is actually made up of matter compared to the entire volume. For us, we're going to do this for our simple cubic system. Again, simple cubic means that we're dealing with a cube. All my lengths are going to be the same, 90-degree angles. and I only have atoms in the corner, or in the corners. And so I'm going to try to draw a picture here. Let's see, we have this face here, and there's a couple ways we could draw it. We could draw it the way that we did before. We kind of draw this transparent thing, and I put dots on each vertex. I don't necessarily want to do that. Instead, what I'm going to do is I'm going to draw this slightly different. And it's good to be able to draw both versions of this. So this is my box. I apologize, I'm not great at drawing. I'm not drawing with perspective or anything like that. So if you've taken art classes or are into art and perspective and all that stuff, I'm sorry. I'm not going to do that. I don't know how. I'm not good. It would just probably end up making it more confusing somewhere along the way. What we have here is I'm going to just say that this here is length A. And length A is going to be the same as the length that goes along left and right, and it's also going to be the one that goes in and out here as well, because again, it's cubic. The next thing I want to do is I want to put my atoms in here. Now, we're going to assume that our atoms are hard spheres. We're going to assume that they are touching each other when they can, because we want these to be as close as possible. And so what I'm going to do is I'm going to say, all right, well, if I have a sphere in this corner, it's actually going to be centered at that vertex, which means it's going to come out of this. It's going to do something kind of like this. Right? It comes out of the unit cell. Well, that's great. I'm glad that we can visualize that's what's happening, but we don't want to do that. We only want to talk about the part that is actually in the unit cell. So I'm going to say that we have part of an atom there. We can see the top of there. So what we're doing is we're seeing kind of this atom sitting here, and it's cut. So this is the inside of the atom here. I'm going to do the same thing with this corner. And the same thing here. So hopefully you can visualize that, but this is that unit cell. It doesn't spill outside of this cube at all. I've put spheres at every single vertex, every single corner of this cube, and then I cut this cube. So these spheres are all cut. They're only portions of spheres at this point. So right now I have two questions that I want to ask myself. Number one, how many atoms do I have? And yes, there are 8 corners. That means there's 8 atoms in general. What I'm really asking though is how many atoms do I have total? Remember, these are only portions of atoms. So if I were to take all of these portions of atoms and then sum them up, how many would I have? And we can look at this and we can see what's happening. If I were to put a box in front of this one, then I'd have a little bit more of this atom here. If I were to put one next to it, I'd have a little bit more. If I put another one here, I'd have more. I'd stack 4 on top. I'd have the whole atom. It might take a second to think about it and to be able to see this, but what we have is we have that 1/8 of an atom are at each corner. And we have 8 corners. And so what that means is we could go through, we could do the math, we could be really good about it. We could say I have 1/8 atom per corner. I multiply that by 8 corners. Corners cancel out. I end up with, well, what's 1/8 over, or 1/8 atoms times 8? I get that we have 1 atom total. So there's 1 atom total inside of this picture here. I do also want to write down a few other things that we're going to need to know. I want to go ahead and discuss the volumes that we're going to have. Up top, I mentioned that one of the things we want to know about the unit cell is we want to know the volume of the cell. We actually want to know the volume of this cube. And so what I want is I want to know V cell. And V cell, in our case, is going to be A cubed. We also want to know the volume of a sphere. And the volume of a sphere is going to be equal to 4/3 pi r cubed. The volume of atoms that I have, I'm just going to write VAT for volume of the atoms, is going to equal the volume of my sphere times my number of atoms. And so lastly, what I'm going to do is I'm going to have my packing density, sometimes called the atomic packing factor. And what that is it's simply going to be the volume of atoms that I have divided by the volume of my cell. So that's really what I'm doing here, and I'm partway there. I already know that the volume of atoms, or the number of atoms that I have this part here. I know the number of atoms that I have. The next thing I'm going to need to do is I'm going to need to figure out what's the volume of each atom individually. To do that, I'm going to need to know what's the radius? What is the radius? And what we're going to do here is we're going to figure out that the radius, this is actually a really nice picture here. This is the easy one. Because we said that these are going to be touching, and we said that these are centered at the vertex, I know that the radius is just going to be half of this. And then there's going to be another radius for this one, and that again is going to be half of A. So I'll go ahead and write that down. We have the radius equals half of A. All right, so now what I can do is I can just plug numbers in, and we can then start simplifying things. Let me get myself a little bit more room here. We're going to use those equations that I had up top, these equations here, along with the fact that we know that there's one atom total, and we know what our radius is now. We have a relationship between radius and A, and that's a good thing, because what we have here is I have one of these in terms of A, I have one of these in terms of R. That's two unknowns. What I want to do is I want to make sure that I only have one unknown. I want to make sure that I only can plug one thing in so that I can solve. All right, so my packing density equals the volume of my atom. And again, apologize for my writing. That's why I'm going to narrate so you know exactly what I'm trying to write. The volume of my atom divided by the volume of my cell is going to be the volume of my sphere times, in this case, one atom, divided by the volume of our cell, which we said is A cubed, right? It's a nice easy one, cube. Okay, so then what I need to do is I need to substitute what the volume of my sphere is. And my sphere is, the equation for that is 4/3 pi r cubed, but we know what r is, so I'm going to make a substitution. I'm going to say that r is 1/2 A cubed. I multiplied this by 1, so I'm just left with atom divided by A cubed. I can start simplifying things, and I get 4/3 pi. I distribute that cubed through, and I get 1/8 A cubed atom per A cubed. I simplify this and I get 4 pi over 24 atom when I simplify this, I actually get approximately 52% of it is atom. That right there is going to be the answer. The idea here is that if I have something in this structure here where I'm in simple cubic, this same picture here, simple cubic, how much is actually going to be atom compared to the entire thing? And in this case, it's 52% atom. That's only about half. And if I were stacking cannonballs or oranges, I'd be wasting a lot of space because I have almost half of my space that's filled with nothing. Really quick, before I finish the video, I wanted to look through some of these images real quick. Here I have the Bravais lattice. I have a link to it here. I'm going to put this in the description, this slideshow, so hopefully you can be able to get that. Look at that for a while. Polycrystals I decided to put into another video, and so we'll skip over that for now. We'll come back to that picture. If you want to take a look at it really quick, you can pause the video and look at it. But I definitely wanted to show you this. What I have here is our different cubic systems. Here we have our simple cubic, one in each corner. I have the picture here of the unit cell using hard spheres. That's what I was trying to draw. This, I think, is much easier to understand what's happening. And then I have the picture here of the entire system, what it looks like if I were to continue that on and show you how the unit cell kind of sits inside of the material and how I could kind of just pick that box up and move it over and I'd have the exact same picture. I have the body centered where I have the white atoms are going to be the ones at the corner, and the only reason that they're different colors right now is just so that it's easy to tell the difference between them. It's not the fact that it's anything different. It's not a different atom or a different molecule. You'll see though, as I stick this in the center, that it spreads apart these ones that are on the edge. So if I wanted to do the packing density for this, I can't just say that my radius is 1/2 A anymore. I'd have to figure out where my points of contact are through here and calculate a new way to correlate my A with my radius. Here's the picture of what it looks like in the actual structure. And then lastly, we have our face centered again, each corner, and then each face has one as well. When we look at the structure, the unit cell, it looks something like this. And again, these corner atoms are actually further apart now than they even were for the body centered. We'd have to find a new way to correlate the length of the cube lengths, the edges of the cube with the radius of these atoms. And again, here's the picture of it.